I'm Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. Today in this video, I'm going to discuss about dielectric materials and some of the terms related to dielectric materials. Now, coming to dielectric materials, so we know that these materials, they have many applications in day-to-day life. And generally, when we say dielectrics, what comes to our mind first is we are talking about insulators. So when we take dielectric materials, first thing that comes to our mind is we'll say that they are good insulators. So we call these dielectric materials to be good insulators. If they are insulators, then why we have to name them or give nomenclature to them as dielectrics, or in what way these dielectrics are different from normal insulators? So when we, what we are going to observe here is, suppose if we take normal insulators, and what we'll observe here is in these insulators, their valence band will be completely filled. So we have many number of valence electrons. Because valence band is completely filled and we have many number of valence electrons, and we know that more the number of valence electrons, they are more strongly attracted towards the nucleus. So that's why it will be difficult for the electrons to come out of their atoms or come out of attraction towards the nucleus and take part in conduction. So that's why these insulators, they do not have any free electrons. And coming to these dielectrics, similarly, they also don't have any free electrons. And if we consider examples of these dielectric materials, we have glass, plastic and mica. So we have glass, plastic and mica. So these are some of the best examples of dielectric materials. Now, when we talk about these dielectric materials, what they are like little bit special compared to normal insulators. So, of course, what comes to our mind when we talk about dielectrics? Dielectrics are insulating materials. And here what we are going to observe here is here number of valence electrons are more. So that's why they are very strongly bound to their parent molecules. And because they are strongly bound to their parent molecules, they cannot come out of that attraction and they don't take part in conduction. So electrons, they cannot move freely. They are very strongly bound to their nucleus. And even if we supply energy, so that energy, it can be in the form of temperature, thermal energy, or it can be in the form of electrical energy, that is applying voltage or electric field. Still we'll observe that these electrons, they cannot come out, and if we go for very high electric field, so there are chances of these materials getting damaged. So this is about our dielectrics being insulators. Now, and also when we talk about some of the properties of dielectric materials, usually we'll say that these are non-metallic materials and resistance of these materials is very high. And when we talk about their resistance, they have one unique property of having negative temperature coefficient of resistance. So it is NTCR, it is called as NTCR. So these materials, they are special in having negative temperature coefficient of resistance. And usually when we talk about the resistivity values, so its range, it falls between 10 to the power of 6 ohm meter to 10 to the power of 16 ohm meter. So it falls between 10 to the power of 6 to 10 to the power of 16 ohm meter. So they have very high resistance. And when we apply very high voltage bias also, there will be very small or negligible current flowing across these materials. These materials, they are going to give very small current even at very high voltages. But as I said, if we try to go to very high voltages, these materials, they cannot withstand such high voltages, and these materials, they may get damaged. So we cannot use them. Now, when we talk about these dielectric materials, they are special. As I told you, they are not just like normal insulators. They are special materials. And what we say is, when we talk about these dielectric materials, they have this property of getting polarized. So these dielectric materials, they have this property of getting polarized when we place them in external magnetic field. When we place them in external electric field. So here, so in what way these dielectric materials are different from insulators? So when we talk about these dielectric materials, when these dielectric materials, when we apply electric field to these dielectric materials, they have this property of getting polarized. Now, what is this phenomenon of polarization? So that we'll come to know when we go for different terms related to dielectric materials. For the time being, what we are saying here is these dielectric materials, once we place them in external electric field, so they have this property of getting polarized, which make them unique compared to normal insulators. And generally, how we'll apply electric field to these dielectric materials? In order to apply electric field, generally what we'll do, we'll place these dielectric materials. So we place these dielectric materials in between the capacitor plates, and then we'll apply electric field. So generally, directly we cannot apply. Let's just take the terminals of external supply and then connect it to dielectrics. So generally, what we are going to do, we are going to place our dielectric material in between the two capacitor plates. We know what is a capacitor. Capacitor, we know it stores charge, and we know that generally and capacitance of a capacitor, it is going to get modified when we insert a dielectric material in between its capacitor plates. So here, if you want to apply electric field, so what we'll do, we'll keep it in between the capacitor plates and then we are going to apply electric field. And we are talking about the polarization. We know that if we take any material, that material is made up of atoms or molecules. So this polarization, it may takes place at atomic state, or it may takes place at ions or atoms, displacement of atoms in a molecule. So there are different types of polarization that also we are going to discuss in my next videos. So here what we are going to observe here is, because of this polarization, whatever charges are present inside the material, and these charges, first of all, they are bonded to each other, but once we apply electric field, then we'll observe that these charges, they get displaced, so they get separated from each other. Then to onto the one side, plane surface of dielectric material will have negative charges, then towards the other side we have positive charges, and this separation of charge is nothing but polarization. And these materials, they have this property of getting polarized once we place them in external electric field. So this is, and obviously here when we talk about polarization, here there is one important term which we are going to discuss throughout this dielectric topic. So here we are talking about electric dipole moment. So these dielectrics, they have electric dipole moment once we apply electric field. So what exactly is electric dipole moment? That also we are going to discuss. And as I said, when we insert dielectric materials in between the capacitor plates, obviously capacitance of that capacitor plate is going to change. And if we want to talk about different types of dielectrics, what we have observed here is vacuum. If we take vacuum, actually vacuum, will say that it's a perfect insulator. It is an insulator. Vacuum is insulator, but it is not dielectric. So there is one quotation when we try to compare dielectrics with insulators, what we'll find here is all insulators need not be dielectrics. This is a very important point. So all insulators need not be dielectric. So that's why when I started to showing you difference between what exactly is a normal insulator and what exactly is a dielectric. So in an insulator, we won't have any free electrons, and electrons are very strongly bonded to their nucleus. But when we talk about dielectrics, apart from not having free electrons, they have this property of getting polarized, and also they'll have some net electric dipole moment. So that dipole moment, it can be permanent or it can be temporarily based on the application of electric field or what type of material we are using for dielectrics. So here, so that's why we'll say that all insulators need not be dielectrics. If you want to go for one example, we can take vacuum. So if we take vacuum, it is a perfect insulator, but it is not a dielectric material. Okay, so this is one example. So if when we try to compare with normal insulators, so these are unique materials, and because of their this property of getting polarized, they've got many applications. So moving further, talking about these dielectric materials. So in order to know much about these dielectric materials, we are going to discuss some of the definitions related to dielectric materials. So till now we were talking about polarization, and of course we are talking about dipole moment. So we are talking about dipole moment. So first we'll try to know what exactly is a electric dipole. So first term related to dielectrics is electric dipole. And here, what exactly is electric dipole? So here in this case, as you can see, I have taken two charges, and magnitude of those two charges, I'm representing them by Q. And what you're going to observe here is these two charges, they are equal in magnitude, but they are opposite charges. So that's why I have taken one charge to be plus Q and then other charge to be minus Q. And if you look at this figure, in this figure, you'll find that these two equal and opposite charges, they are not coinciding with each other, but they are separated by a small distance r. So in some contest, we can also take this distance of separation to be small d. So here what we are going to observe here is these two charges, they are separated by very small distance. So r is very, very small. They are separated doesn't mean that they are very much far away from each other. So these two charges, they are separated by a very small distance, and that distance we are taking it to be r. So such a system where we have two equal and opposite charges separated by a small distance is nothing but our dipole. And we try to define our dielectrics in terms of dipole. So we can say that once we apply electric field to a dielectric material, then there will be formation of many dipoles inside the dielectric material because of separation of these charges. Now, when we have such electric dipole, when we have a system of two equal and opposite charges separated by a small distance, then there is some dipole moment associated with such dipole. So, and usually what is the notation we are going to take for this electric dipole moment? It is represented by mu. So, when we have such two equal and opposite charges separated by a small distance r, then their electric dipole moment, which is given by notation mu, it is simply product of two parameters. So what are those two parameters? One is charge and second one is distance between those two charges. So if you come back to this figure, so what is the magnitude of these charges? It is Q into, and of course they are separated by a small distance r. So this charge into distance between two charges will give us electric dipole moment. And coming to units, as you can observe here is Q. We have our Q. Q is charge, and we know that units for charge is coulomb. And because they are separated by distance, and if we consider MK system, the distance of separation, it will be in meters. So what is the unit for electric dipole moment? Units are coulomb meter. Now units, they play a very important role when we talk about of course physics parameters. So in this slide, in this PPT, we have discussed about two terms related to dielectric materials. One is electric dipole, another one is electric dipole moment. Okay, so electric dipole, two equal and opposite charges separated by a small distance, whereas when we talk about electric dipole moment, when we have such a system, then product of magnitude of charge and distance between two charges will be electric dipole moment. Then moving further, so here when we talk about dielectrics, generally there are two types of dielectric materials. Now we are going to discuss about different types of dielectric materials. So if we take, so here we are going to discuss about different type of dielectrics. And what we are going to observe here is when we try to discuss different types of dielectrics, generally there are of two types. So first type, it is called as non-polar dielectrics, and second one, it is called as polar dielectrics. So second one, they are called as polar dielectrics. So one is non-polar dielectric and other one is polar dielectric. So first we are going to discuss about non-polar dielectrics. So in order to have better understanding about non-polar dielectrics, first we'll try to understand what exactly is non-polar molecule, because non-polar dielectric, it consists of non-polar molecules. Now, in order to understand this concept of non-polar molecule, what we have done, we have taken a dielectric material. In the dielectric material, if we consider an atom, we know what exactly is an atom. Suppose if we try to define in terms of its nucleus and electrons, we know that when we take an atom, in an atom we have positively charged nucleus. So this is our positively charged nucleus, and then after that we have our electrons revolving in various orbits around the nucleus. And when we talk about nucleus, we have two types of particles. One is our neutrons, another one is protons. Neutrons does not have any charge, and when we talk about protons, they are positively charged. And as you can see here, as we have these electrons revolving in various orbits, what we can consider here is this electron distribution. So we have distribution of electron in various orbits, and this distribution of electrons in various orbits, it is defined in terms of electron cloud. So here we are going to talk about electron cloud. So these electrons revolving around the nucleus in various orbits, they are taken as electron cloud. And what is the shape of this electron cloud? We know that shape of an atom is spherical. So atom shape, it is assumed to be spherical in nature. So obviously this particular electron cloud, it will be spherical in shape. So here when we talk about atom, what we are going to observe here is we have positively charged nucleus. So when we take an atom, we have positively charged nucleus, and of course we have electrons revolving in various orbits. And if we consider it as a spherical electron cloud, so this is our electron cloud which is surrounding our nucleus. So this is our electron cloud which is surrounding our nucleus. So this is our spherical electron cloud. And talking about this one, this is our positively charged nucleus. So we have our positively charged nucleus, and what we are going to observe here is center of this nucleus and center of this electron cloud, they are at the same point. So if we take our atom, so in an atom, when we consider center of nucleus and center of this spherical electron cloud, they occur at same point. Okay, so if you see an atom, we can say that positive charge of nucleus, let us suppose that it is concentrated at a single point, and let us call that single point as center of gravity of positive charge. And similarly, negative charge of electrons, it is supposed to be concentrated at a single point, and let us call that single point as center of gravity of negative charge. So this has to be negative. So center of gravity of negative charge. So what is center of gravity of positive charge and center of gravity of negative charge if we consider an atom? So we'll observe that a positive charge of nucleus, it is concentrated at single point, and that single point, it is called as center of gravity of positive charge. Similarly, if we consider spherical electron cloud, so center of spherical electron cloud, it is again assumed to be concentrated at single point, and it is called as center of gravity of negative charge. So if we consider non-polar molecule, so in that molecule, if we take an atom, we'll observe that positive charge of nucleus, it is concentrated at single point, and that single point, it is called as center of gravity of positive charge. Similarly, if we take our spherical electron cloud, it is also concentrated at one single point, and it is assumed to be center of gravity of negative charge. So what we are going to observe here is, in case of non-polar molecule, these two center of gravity coincide. So these points, center of gravity of positive charge and center of gravity of negative charge, they are not separated by a small distance. So that's why they are not in the state of electric dipole. So that's why they don't have any dipole moment associated with them. And such a molecule, it is said to be non-polar molecule. So because they don't have any dipole, and because there is no separation of the charges, so we can say that these non-polar molecules, they have symmetrical structure because there is no displacement of their center of gravities, and because there is no formation of dipole, so obviously there is zero dipole moment associated with non-polar molecule. And some best example, in order to understand this non-polar molecule, we have hydrogen, nitrogen, oxygen, and then of course carbon dioxide as well as benzene. So if we take two hydrogen atoms which come together by sharing electrons to form covalent bonds. So when we consider those two hydrogen atoms, so here there is no separation of charges. So that's why what we are going to observe here is there is no dipole. So that's why there is zero dipole moment associated with hydrogen, nitrogen, oxygen, where they are coming together and forming covalent bond by sharing either single or many pairs of electrons. So coming back to non-polar dielectrics. So these non-polar dielectrics, as we know that they consist of non-polar molecules. So and here generally these non-polar dielectrics, they consist of monoatomic materials. So to just one, if you want to name example, just like our silicon crystal, which is made up of single silicon elements or atoms. So like that, generally non-polar dielectrics, they consist of single atoms, and here what we are going to observe here is center of gravity of negative charge and center of gravity of positive charge, they coincide. So these materials, they have symmetrical structure, And here two equal and opposite charges, they are not separated by a small distance, so there is no electric dipole moment. So as you can see, if we come back why their electric dipole moment is zero, we know what is the formula for electric dipole moment. It is charge into distance between two charges, and because they are not separated, their centers are coinciding, so this distance of separation will become zero. So that's why here electric dipole moment is zero. So such dielectrics, they are called as non-polar dielectrics. But same non-polar dielectrics, when we place them in external field, so when we place such non-polar dielectrics in external field, they will get polarized. So centers of positive and negative charges, they will be displaced by a small distance. So here we'll have some dipole moment once we place them in external electric field. So these dielectrics, they will become polarized, but for that we need to apply electric field. But on the normal condition, when we are not applying any electric field, so we can say that there is no dipole inside those dielectrics, so that's why dipole moment is zero. And these molecules of these materials, they have symmetrical structure. So here now we are going to discuss about second type of dielectric materials. So the second type of dielectric materials, they are called polar dielectrics. So we have our polar dielectrics. So obviously when we have discussed about non-polar dielectrics, we have our polar dielectrics. So obviously in polar dielectrics, centers of positive and negative charges, they are separated by a small distance. So first we'll try to see what exactly is a polar molecule. So obviously polar dielectric, it consists of polar molecules, and if we take this polar molecule, what we are going to observe here is they have unsymmetrical structure. So we have discussed about non-polar dielectrics, they have symmetrical structure, but coming to polar molecule, they have unsymmetrical structure. Why they have unsymmetrical structure? Because center of gravity of positive and negative charges do not coincide, they are separated by a small distance. So here what we are going to observe here is centers of positive and negative charges, they are not occurring at the same point, they do not coincide, but they are separated by a small distance. So that's why these molecules, they have unsymmetrical structure. And because center of gravity of positive and negative charges are separated by a small distance, so obviously each molecule, it is in the state of electric dipole, then there will be dipole moment associated with such molecules. So such type of molecule, they are called as polar molecules. And if you try to consider some of the examples of these polar dielectrics, we have our water. So here we have water, H2O, and then most famous polar dielectric is hydrogen chloride, and then carbon monoxide, nitrogen, ammonia, etc. All these, they will come under polar molecules. So what is our polar dielectric now? So obviously in polar dielectric, it consists of polyatomic molecules. So whereas in case of non-polar dielectrics, they consist of monoatoms. So or even if you take your molecule, that molecule, it consists of same type of atoms. So like we have taken hydrogen. So hydrogen molecule, if you take, it consists of same type of hydrogen atom. So here, but whereas when we talk about polar dielectrics, so in polar dielectrics, if we consider their molecule, it consists of different types of atoms. Suppose if you consider our water, it consists of two types of atoms. One is hydrogen and other one is oxygen. And when we have such polyatomic molecules, what we are going to observe here is center of gravity of negative charge may not coincide with center of gravity of positive charge. And this negative and positive charges, they are separated by a small distance. So each molecule, it is in the state of a dipole. So they have dipole moment. So each molecule, it is in the state of a dipole moment. So such type of dielectrics, they are called as polar dielectrics. Now, here coming to this non-polar and polar dielectrics, when we try to consider difference between these polar and non-polar dielectrics, so first thing is what we are going to say, if we take non-polar dielectrics, their molecules have symmetrical structure, whereas polar dielectrics, they have unsymmetrical structure. And usually non-polar dielectrics, they consist of molecules, and these molecules, they have same type of atoms, whereas polar dielectrics, they consist of molecules which consists of different types of atoms, or we can also call them as polyatomic molecules. And then next thing is here, when we talk about these non-polar dielectrics, in non-polar dielectrics, centers of Center of gravity of positive charge and center of gravity of negative charge, they coincide. And whereas in polar dielectrics, the center of gravity of positive and negative charges, they are separated by a small distance. So that's why in non-polar we have no dipole moment, because they are not separated. Whereas in polar dielectrics, there is some dipole moment associated with each molecule. And here, of course, examples also we have taken. So this is about non-polar and polar dielectrics. But if we consider even polar dielectrics, when we are talking about its polar molecule, we are saying that it has got dipole moment because their centers are separated by a small distance. But if I consider net dipole moment, here we are talking about just molecule. When I take each molecule of polar dielectric, each molecule it will have dipole moment. But if I consider net dipole moment of entire polar dielectric, this will be 0. So this point is very, very important. So if I take polar dielectric, then net dipole moment. So net dipole moment of entire polar dielectric. So if I consider entire polar dielectric, so net dipole moment of entire polar dielectric is 0. This is very, very important. So why it is 0? Because dipole moment vector of each molecule of polar dielectric, if you take, they will be oriented. If I consider all the molecules, each molecule it will have its one direction of electric dipole moment. Then other molecule it will have its direction in some other way. So all these molecules which are in dipole states, they are randomly oriented. Because they are randomly oriented, then what we are going to observe here is the net dipole moment is 0. So, when we talk about the overall dipole moment, even if we consider non-polar or polar dielectrics, the net dipole moment is 0, of the material is 0. But we can make the dipole moment exist, or we can they can have net dipole moment when we place them in external electric field. So we can polarize both non-polar as well as polar dielectric by placing them in external electric field. Now we'll try to understand how, if each molecule of polar dielectric, their center of gravity of positive and negative charge, they are separated by a distance. So in order to understand this, first I have taken example. Of course, let us take H2O, or also we can take HCl. So first I'll talk about hydrogen chloride molecule. So if we take hydrogen chloride molecule, we know that hydrogen, it has got single atom, and then chlorine, what it will do, it will also give it single electron. So it will give it single electron. Now this hydrogen, it has configuration, of course its atomic number is 1, and it needs 1 electron to gain stable configuration. Chlorine, its configuration is 17, and it also needs 1 electron to gain stable configuration. So what this hydrogen atom and chlorine atom will do, they'll come together and they'll share single pair of electron. So they'll come and share single pair of electron, and then they are bonded to each other strongly. Okay, so and this type of bond, actually this will not come under covalent bond. This type of bonding, it is called as hydrogen bond. And what we are going to observe here is mostly many of the cases, polar dielectric materials, generally they have hydrogen bond. So which consists of one hydrogen atom, and other one is highly electronegative atoms like chlorine, bromine, oxygen, nitrogen, etc. So if we consider this hydrogen and chloride, as I told you, both of them, in order to get stable configuration, they'll come together and they'll share single pair of electrons to form single covalent bond. But we know that compared to hydrogen, this chlorine atom is highly electronegative. So this chlorine atom, it is highly electronegative. Now what do you mean by highly electronegative? This chlorine atom, it will try to pull this pair of electrons towards it. So it has this intensity of attracting electrons. So what it will try to do, it will try to attract this pair of electrons towards it. It doesn't mean that it is completely taking away that pair of electron. Just this pair of electron, it will get little bit displaced, and it will try to just come closer to chlorine atom. Then what happens to chlorine atom? Chlorine atom will become partially negatively charged, and hydrogen atom, it will become partially positively charged. Why? Because this pair of electron, it has gone closer to chlorine atom because of its high electronegativity. So there is development of partial charges. So why we are taking partial charges? Because chlorine, it is not completely taking away this pair of electron. Just it is pulling it little bit closer to it. So that's why now hydrogen, it is in the state of partially positive, and chlorine atom, it is in the state of partially negative. Now this hydrogen atoms, it will act as a positive end of dipole. So it will act as positive end of dipole, whereas this chlorine atom, it will act as negative end of dipole. So this will act as negative end of dipole. So as you can see here, we have positive and negative charges separated by a small distance. So such molecule which is in the state of dipole, even when we have not applied external electric field, such a molecule, it is called as polar molecule. This is how we are going to have dipole in polar molecule even when we are not applying external electric field. And same is the case with water. So if we consider water, in water also we have one highly electronegative atom, oxygen, and we have two hydrogen atoms. And we know that this oxygen, it is going to share two pairs of electron with these two hydrogen atoms. And this oxygen, because it is highly electronegative, it will try to pull that pair of electrons towards it. So as a result, this oxygen atom, it will act as negative end of the dipole. And these hydrogen atoms, they'll act as positive end of the dipole. And similar case we have observed in case of ammonia. Of course, I have discussed about hydrogen chloride, and also we have this CH3, Cl also. Here also it is the same case. So here I think for now we came to better understanding how polar molecule will be in the state of a dipole and why there is dipole moment associated with polar molecule. So these are about the different types of dielectrics. Now then next, as still we are proceeding with basic definitions related to dielectric materials. So here we have permittivity of a medium. So medium. So when we talk about a medium, we are talking about a material. So medium is nothing but a material. If you take a material, especially here we are talking about a dielectric material, and nature of dielectric material, it is given by one parameter. That parameter, it is called as permittivity. So what exactly is permittivity? So permittivity, it indicates easily polarizable nature of the material. Once I apply electric field to a dielectric material by placing it in between the capacitor plates, how easily the dielectric material is getting polarized, because some dielectrics, they'll get easily polarized, whereas some other dielectrics, they'll getting them polarized, we have to go for high electric field. So depending upon their polarization process, whether it is easy or difficult, their permittivity value is going to change. So once we place them in external electric field, easily whether there is separation of charges or we have to go for very high electric field for charges to separate, based on that permittivity of a material, dielectric material or medium is going to change. And that permitting, so what is permittivity is nothing but permitting separation of charges within the material. And usually what is the notation used for permittivity of a medium? It is represented by epsilon. So epsilon, it is the notation for indicating permittivity of a medium. And when we consider permittivity of vacuum or free space, so its value is 8.854 into 10 power of minus 12 farad per meter. So what is the unit for permittivity of a medium? It is given by farad per meter. So even vacuum, it has got some permittivity, and that permittivity, of course, it actually we can take this as constant value. So epsilon naught, usually it is denoted by epsilon naught, and what is its value? 8.854 into 10 power of minus 12 farad per meter. So this is about the permittivity of a medium. And then coming to our next definition related to dielectric material, capacitance of a capacitor. Now, why we need to discuss about a capacitor or its capacitance? Because already I told you that dielectric materials, they get polarized when we place them in external electric field. So directly we cannot take terminals of a battery and just connect it to dielectric material. So what we are going to do in order to apply electric field, we are going to keep our dielectric material in between the capacitor plates. So we are going to place dielectric material in between the capacitor plates, and then we are going to apply electric field. So because here there is role for capacitor plate, so obviously we should have some knowledge about capacitance of a capacitor. And what exactly is a capacitor? We know that when we consider a capacitor, we have two parallel plates, and they are of same area, and of course they are separated by a distance, and they are generally connected to external electric field. And what happens once we apply electric field to these capacitor plates, we'll see that there will be development of charges on the capacitor plates. So these are the charges which are developing because of this external electric field, and this is the direction of electric field applied. So what we are going to do here is, because there are charges, development of charges on the surface of capacitor plates, we can call a capacitor to be a, of course, other name for capacitor is also, we can call it as conductor. And what it is going to do, it is going to store electric charge, because there is development of charges on application of electric field, right? So they are going to store electric charge. And how to define capacitance of a capacitor, to how much extent it is going to store charge, it is given by capacitance, and usually it is denoted by capital C. And how it is given, it's a ratio. What is that ratio? Ratio is Q stands for charge, V is potential difference, that is created because of formation of opposite charges on surface of capacitor plates. So charge per volt is the definition given for capacitance of a capacitor. As you can see, what is Q here? Q is charge on the capacitor plates, and V is potential difference between the capacitor plates. And what is A? A is area of, there is one more formula for capacitance. So it is also given by A epsilon by D. So what is the another formula for capacitance? A epsilon by D, and an epsilon we know. Epsilon is permittivity of the medium which is present in between the capacitor plates. So here, suppose if we insert a dielectric material, and the dielectric material, it has got its permittivity epsilon, then its capacitance, it is given as A epsilon by D, where A is area of capacitor plates, and of course, as I said, epsilon is permittivity of dielectric material which is inserted between the capacitor plates, and D is the distance of separation between the capacitor plates. And what's the unit for capacitance? It is given by farads. And one thing what we have to understand here is capacitance of a capacitor without dielectric, and when there is no dielectric, usually we'll take it as A epsilon naught by D, where epsilon naught is permittivity of free space. So, and whereas capacitance of a capacitor with the dielectric, when we place dielectric, those values are completely different. It means that when we insert dielectric material in between the capacitor plates, its capacitance value is going to get disturbed. Then, of course, till now we were talking about polarization. Now, in order to have better understanding about what exactly is this electric polarization, I have taken this figure. So, as you can see here, I have a dielectric material. So this is our dielectric material, and this dielectric material, it is placed in between these two capacitor plates, and we have applied electric field. This is the direction of electric field applied. Okay, now first, once we apply electric field, what will happen? First, charges are developed on the surface of capacitor plates. So as you can see, this capacitor plate, it has become positively charged, and this capacitor plate, it has become negatively charged. So this is positive polarity of external electric field, and this is negative polarity. So obviously this plate, it will become positively charged, and this plate, it will become negatively charged. Now in between these capacitor plates, we have inserted dielectric slab. Okay, so dielectric material. Now we know that once we apply electric field to a dielectric material, what happens inside the dielectric material? Their charges, there will be separation of positive and negative charges. Now what you are going to observe here is, suppose I have taken each molecule of this dielectric material. Suppose this is one molecule. Okay, suppose here dielectric material chosen is hydrogen chloride. Then we know that this hydrogen chloride, here this hydrogen, it is in the state of positively charged, and chlorine, it is in the state of negative. Okay, so now all these negative ends, which are chlorine ends of hydrogen chloride molecule, their direction, it will come towards this positively charged capacitor plate. So all negative charges, they get accumulated onto the left side or towards the positively charged capacitor plate, and whereas this hydrogen atoms, which are positively charged, because of their attraction to this negatively charged capacitor plate, they get accumulated onto the right end face. So as you can see, Now this negative and positive charges, they are separated by a small distance, and we can make out that all negative charges, they are in one particular direction, all positive charges of different molecules, they are in one direction, and you can see that each molecule, it is in the state of a dipole. So throughout the dielectric material, there are many dipoles forming. Such process of forming dipoles throughout the dielectric material, when we place a dielectric material in external electric field, is nothing but electric polarization. In order to understand this concept of electric polarization, we have this particular figure in this given in this slide. Okay, so here, if this is the direction of electric field, and so as you can see, so when we apply electric field to a dielectric material, in which direction positive charges will move? Positive charges move in the direction of field. As you can make out that there is accumulation of charges here onto the right end face of dielectric. And what is the direction of electric field? In the same direction. So that's why when we apply electric field, usually within dielectric material, we'll observe that all the positive charges, they get displaced in the direction of field, and negative charges in the direction opposite to field. So there is formation of dipoles due to displacement of charges throughout the dielectric. Once we apply electric field, this phenomena, it is called as electric polarization. Then coming to next term, dielectric constant or relative permittivity. So we know about permittivity. So permittivity, it is denoted by epsilon, and we have seen that once we place a dielectric material in between the capacitor plates, how easily it will permit polarization within it. Whether a material is easily polarizable, or we have to go for very high fields in order to polarize it. Based on that, we have different values for different dielectric materials, permittivity values. Now, what is relative permittivity? So, in this case, what we are going to do, we are going to compare permittivity of a given dielectric with permittivity of vacuum or free space. So, what is a relative permittivity or dielectric constant? As you can see, relative permittivity, it is given as epsilon r. Sometimes this relative permittivity, it is also given by notation K. So dielectric constant or relative permittivity, they are given by two notations. One is dielectric constant K or relative permittivity epsilon r. So if you try to take the definition, what is the definition? As you can make out that it's a ratio. And what we have in this ratio, we have permittivity of medium to the permittivity of free space. So ratio of permittivity of medium to the permittivity of free space is nothing but relative permittivity. So we are comparing permittivity of a material with respect to permittivity of free space. That's why the term relative permittivity. And this relative permittivity can also define in terms of capacitance as C by C naught. What is C? C is capacitance of a capacitor with dielectric, when there is dielectric material in between the capacitor, and C naught is capacitance of a capacitor when there is no dielectric material in between the capacitor plates. And because here we know that permittivity units are farad per meter, and this epsilon naught is also having farad per meter. Or if you take this definition in terms of capacitance, farad, so they'll get cancelled. So that's why this dielectric constant or relative permittivity, it has no units. And if you consider air, suppose if you are filling air in between the capacitor plates, what is the dielectric constant of air? It is taken to be 1. So coming to next definition, polarizability. And usually what is the notation used in order to represent this polarizability? Alpha. So now what we are saying here is, when we take our dielectric material, so if you go back to our figure of electric polarization, as you can see here, the separation of charges, it is not taking place in the absence of electric field, but these charges are getting separated when we are applying external electric field. It means that what this electric field is doing, it is inducing some force on these charges so that they get separated. And because these dipole formation is taking place on application of external field, so that's why whatever dipole moment is associated, it is called as induced dipole moment. Why it is called induced dipole moment? Because this dipole moment or formation of dipole is taking place because of application of external electric field. And depending upon strength of electric field, suppose if you apply weak electric field, then all dipoles may not get polarized. If you go to very high electric field, then all dipoles may get polarized. So induced dipole moment, it is proportional to strength of electric field. So here we'll say that induced dipole moment is proportional to strength or intensity of electric field. So mu is proportional to E, and if I take out this proportionality sign, then I'm introducing one proportionality constant alpha, and this alpha is nothing but polarizability. And if I take this relation, from this relation, how we are going to define polarizability? It's a ratio, and what we have in this ratio, induced dipole moment per unit electric field applied. So this is the definition for polarizability. Now coming to units for polarizability, units is farad meter square. Then next we have our polarization vector. So what is polarization vector? Now here we are talking about vector. We are not talking about phenomena of polarization, but we are talking about polarization vector P. How we are defining this polarization vector P? As you can see that it is defined in 3 different ways. And usually what is the notation for polarization vector? We'll take P, on top of it we are going to put one arrow. So this is the notation for polarization vector. And what is the first definition? First definition, it is given as Q dash by A. What is Q dash? Q dash is charges, induced charges when we apply electric field, charges which are developing on application of electric field. So these are called as induced charges, and they are given as Q dash. So what you can say here, also we can call it as polarized charges or induced charges. We know that in a dielectric material, only if we apply external electric field, then charge separation is taking place. So that's why we call those charges to be induced charges. And induced charges per unit area of dielectric is nothing but polarization vector. And then there is one more definition for polarization vector. It is taken as dipole moment per unit volume of dielectric. So what is V here? V is unit volume of dielectric. And suppose if we have considered a dielectric material which has got n number of atoms or molecules per unit volume, and mu is induced dipole moment, then how we can define our polarization vector? It is simply product of this number of atoms or molecules per unit volume into induced dipole moment. Then coming to units for polarization vector, it is taken as coulomb per meter square. And next, electric susceptibility. So electric susceptibility of a dielectric material, it is represented by this symbol chi. So there is difference between psi and chi. So this symbol, it is chi. And we know that induced dipole moment is proportional to intensity of electric field. So obviously this, because the polarization vector is proportional to dipole moment, so even this polarization vector, it is also proportional to electric field E. And if we take out that proportionality sign, then what we are going to observe here is, in terms of this electric susceptibility proportionality constant, our polarization vector, it is given as chi epsilon naught E. And from this, what is the definition for chi? Chi is simply a ratio where we have polarization vector and what we have in the denominator, electric field. So this is the definition for electric polarizability. It is defined as polarization vector per electric field applied. Then coming to our last definition, that is electric flux density or electric displacement, and it is given by notation D. So electric flux density, it is defined as number of flux lines. So here how many, when we place a material in external electric field, so just like magnetic flux, we'll have our electric flux, and how many number of electric flux lines are crossing a surface normal to the lines divided by the surface area is nothing but flux density. So suppose when we talk about a point charge, suppose if I have a point charge, and that point charge, if its magnitude is Q, okay, then if I try to find what is the electric flux density at one particular point, suppose this is my point, and at this point I want to know what is the flux density, and this point, it is separated by a distance r. It is a distance r from this point charge. Now if I try to measure what is the electric flux density because of this point charge, which is at a distance r, then how it is given? It is given as charge divided by 4 pi r square, that is surface area. So, so here it is taken as 4 pi r square. So this is nothing but our electric flux density. But we know that, of course, so 4 pi r square is surface area of a sphere. So because we are saying it's a positive charge, so we are trying to find its flux density in the perimeter of sphere. and that sphere we are considering at distance r, so this will become radius of the sphere. So then flux density is given by this formula. And when we try to express this flux density in terms of electric field, we have to take a definition for electric field. Electric field, it is taken as charge by 4 pi epsilon r square. But we know that q by 4 pi r square is nothing but our d flux density. So obviously what is our electric field? It's a ratio of electric flux density to the permittivity. Now from this, what is the formula? Very important formula. This will be using in later relations associated with dielectric materials. So electric flux density, it is given as epsilon E. What is epsilon? Permittivity of dielectric material. And we know that relative permittivity, it is taken as ratio of permittivity of medium to the permittivity of free space. So from this, what is the permittivity of medium? Simply product of relative permittivity into permittivity of free space. So this particular relation is very, very important. So today we have discussed about dielectric materials, different type of dielectric materials, and of course many terms related to dielectric materials. I hope this session is useful for you to understand more about the dielectric materials. I'm going to end my session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.